I would say butane has a chemical symbol of C4H10. And what this means is that it has a carbon and a hydrogen. It has 3 carbon molecules and 8 for propane, 8 hydrogen molecules. And this is why we call these hydrocarbons, clearly. And it has a heating value of 3,200 BTUs per cubic foot. Its relative density as a gas is 2, meaning it's very much heavier than air as a gas. Another couple of things on some of these. The boiling point for natural gas. For natural gas, the boiling point is minus 256 degrees Fahrenheit. Meaning, if it's a liquid and any temperature above that, that liquid will vaporize. For propane, the boiling point is minus 40 degrees Fahrenheit. And butane, the boiling point, and what this means is when it's a liquid and it will turn to a vapor, and that is at 32 degrees Fahrenheit. So for all you smokers out there, if you're ever on a cold day and you're outside trying to light your lighter and it doesn't work, you got to heat it up. You got to warm up that little container before you strike the lighter, because it has to be above 32 degrees Fahrenheit for it to vaporize. So that's partly why. There's a bunch of information. All right. So the objectives we're going to do today is we're going to perform temperature conversion calculations, state the specific heat values for water and air, define latent heat and state the latent heat values for water, ice, steam, and propane, and calculate sensible and latent heat values. That's what we're going to be doing today. Any questions? Everybody all right? Here we go. So heat and temperature. Heat is a form of energy that transfers from one body to another. Okay? Heat always flows from the hotter object to the cooler object. We already know this. The definition of heat is temperature is a measurement of kinetic energy, or sometimes, oh, there it is, molecular movement. I think we discussed that already. And how do we measure that molecular movement? We use a thermometer. Right? We measure how much molecular movement there is, and that is based upon temperature. Now, this, what sometimes they talk about, if you have a cup of water and a bucket of water and both have a temperature at 20 degrees Celsius, if they both have the same temperature, do they both have the same amounts of potential heat energy? No, the bucket of water contains more heat energy because it's more mass. There's more source there. Now, in sources of heat, we have several different kinds of sources of heat. Of course, our sun is the biggest one. There's several others in geothermal, chemical, nuclear, electrical, mechanical. Listen, everything we do creates heat, clearly. And this is part of the reason why our Earth is heating up, because humans just create heat in everything and anything we do, right? And we just can't help ourselves. That's how it works. Now, they go on to talk about the thermometer and how it works. There's two dudes that created these thermometers, Fahrenheit and Celsius. And so we need to know both. The Celsius thermometer was done by Anders Celsius, and he started at 0 for freezing and 100 to the boiling point, which is very good. I like that. It works really well. However, the other dude used the other thing. He said, let's start at 32 and we go to 212. So we need to know both of these things, right? So in this picture here, as you can see, 32 and 0 are at the same. So this is imperial and this is metric. And it's something important to point out here that I can have water at 32 degrees Fahrenheit or 0 degrees Celsius. I could have ice at 32 degrees Fahrenheit and 0 degrees Celsius. This is called the freezing point or melting point. You could have ice or water at these temperatures. And similarly, I could have water at 100 degrees C or 212 degrees Fahrenheit, and I can have steam at 100 degrees C or 212 degrees Fahrenheit. It's either or. This is called the boiling point, but I could have water or steam at these temperatures, okay? It takes a certain amount of heat to change one from the other, and we're going to discuss that at length. But first, we're going to talk about temperature conversions. And these are the two formulas you can use to convert temperatures. And to make sure that they work correctly, if I had 212 degrees Fahrenheit, and I wanted to find out how many degrees Celsius that is, I will use this formula. What you do is you take your degrees Fahrenheit, which is 212, minus off 32, and that's in brackets, so you have to do that first. You have to do that operation completely first. So that's 180, and then it says divide it by 1.8. Look at that, 100 degrees C. So it works. That formula works. You need to have these in the back of your mind at some point somewhere. I will ask you a question or two on a final exam on converting Celsius to Fahrenheit. So if you ever get to the point and you forget both of these, know that 212 is equal to 100 and 32 is equal to 0. So you can have a comparison. Yes, you have a kind of a comparison to know where you're landing at that. Any questions? Stop me anytime if you do have a question, please. Now, they go on to give you a couple of examples here. Just keep those in mind. I'm not going to really go through them. It's pretty simple, I believe. And now brings us to this temperature scale. As we should know a couple of these already, water is most dense right at this location. That's where water is at its most heaviest. Yes. Down here, this is what I want to point out. At 0 degrees Fahrenheit, that would be equal to minus 17.77. Now, this is where the salt on roads stops working. This is where road salt stops working, okay, at that temperature. So at about minus 18 degrees Celsius, when it's that cold outside, know that the road salt is not going to help you. It's not going to melt the ice. It's just going to be frozen out there. So drive safely. Down here, we call this absolute zero. In absolute zero, we can make the assumption that this would be Rankine, Rankine, or Kelvin. So those are two words that you will need to know for next year. In third year gas, we cover this stuff, and we do gas variations on that, because temperature and absolute temperature comes into our calculations for gases. And you should know that in between zero and the melting point and the boiling point, there's 100 different degrees, and from the melting point to the boiling point on the Fahrenheit scale, it's 180 degrees difference between the two. Just moving along here. We're talking about, in this one, we're talking about what's the difference between temperature and temperature change. We use this little delta T to give us what a temperature change is. Now, for example, if I had minus 18 degrees Fahrenheit and I go up to 32 degrees Fahrenheit, what is the delta T between these two? Well, the delta T is actually 50 degrees is the delta T, yeah? It's the temperature difference between these two. You do have to go through the zero here, and it's all additive. Do we understand that? Is that pretty easy? It's pretty straightforward. It's the difference between the temperatures. Excellent. And then we have a little table called nice to know temperatures. And I think it was Logan that asked me about these, and I thought it was in the other ILM, but here they are in this one. So here's your body temp, right? 37 degrees C or 98.6. Listen, room temperature, not in my house. My partner, my wife, likes it a little warmer than 70 degrees, you know, so I usually sweat. She's fine, but there we are. Hot water, setting for a hot water heater. This is domestic use. When I say domestic use, I mean it's personal use for you and me, etc. Now, how come we don't go any lower than that? Does anybody know? Legionnaires. If water is allowed to sit in a heated spot that does not move, when the water becomes stagnant, so say you go away on holidays, you shut off your water and then you leave, but your hot water tank is still kind of percolating away, you can create bacteria in there, okay? And it's not good for you. It can make you sick. It won't kill you, but it can make you sick. So we need to have our setting a little bit above or right at 140 to prevent that from happening. And where this happens, like I said, if you go on holidays and you close your water valve and your hot water tank is able to maintain that temperature, you will have thermal expansion happening in all your pipes. You ever turn on your cold water and it's hot? That's where the thermal expansion is happening, right? And you're not, and that water can get at a tepid temperature without moving, and you could create some bacteria in it. A normal boiler is about 180 degrees Fahrenheit. Maximum temperature for a low pressure steam boiler, 15 PSI is the pressure max. And there's the temperature for that. I'm sure Marty's going to tell you all about those at some point in your heating class. Okay. Any questions? Still going on? Excellent. Then they give you this. All right. We're not going to be concerned with that. You can do that later. We're going to go on to objective 2. Now, we're going to talk about specific heat values of water and air. So energy is the ability to do work, and it comes in many forms. And we talked about electrical, mechanical, they even have sound, atomic or nuclear, solar, heat energy. So all forms of energy and work, including heat, are measured in kilojoules, kJ, or BTUs. This is metric. And this is imperial. So when I say imperial measurement, it's BTUs. When I say metric, it's in kilojoules. Just so you know, we will be doing both of these. So it says in here, the addition of heat increases the motion of molecules in a substance, which in turn produces a rise in temperature. It's pretty straightforward. In some cases, molecular motion may be increased enough to cause a change in state. Now, as we move forward, we're going to calculate these changes of state and how much heat is required to do that. So in other cases, molecular motion may be increased only slightly, so the molecules are not making the energy leap. So change of state, meaning it changes from one form of another. So ice to water or water to steam, etc. We're going to call that one latent heat. And the last one here where it says not changing the state. So we're just heating something up. And if we're just heating up a substance, we're going to call that sensible heat. So units of measurement in heat energy, we know that 1 BTU is the amount of heat requires the temperature of 1 pound of water by 1 degree Fahrenheit. We know that. So a kilojoule then is a unit of measurement approximately equal to a BTU. It's close, but what it is, it's the amount of heat to raise the temperature of 1 kilogram of water by 1 degree Celsius. And that is 4.2 kilojoules. So here we go. Sensible heat. By definition, sensible heat is a change in temperature only. That's it. Just the change in temperature. And we need a lot of this. In our industry as plumbers and gas fitters, sensible heat is extremely important to us. Okay. We want to know how many BTUs or how many kilojoules it takes to raise the temperature of all kinds of substances. Air, water, steam, etc. It's just one substance raising the temperature. So we could be raising the temperature of steam. We could be raising the temperature of water. We could raise the temperature of air, right? All of those things. So that brings us to something called specific heat capacity. And this specific heat capacity, I am going to write it like SHC when I write it down. So that'll be a little abbreviation of that. This is for all intents and purposes, a multiplier. This is a multiplier that we will use to calculate how much heat it takes to raise the temperature of a substance. Okay, we're going to use this multiplier. Now, in this multiplier, through experimentation, we gave heat values for all different kinds of substance, and these are called specific heats. And here's the definition. The specific heat capacity of a substance is the quantity of heat required to change the temperature of 1 unit of mass by 1 degree. So 1 unit of mass by 1 degree. Now, it's not specific in imperial or metric, is it not? It's a blanket statement, and we will have 2 different versions for imperial and metric. Now, what this means is that it takes 1 BTU per pound, 1 pound per degree Fahrenheit, right? That's what it says in here. 1 BTU to change 1 pound of water by 1 degree. And then similarly, for metric, it takes 4.2 kilojoules per kilogram per degree Celsius. These are the specific heat capacities for water. This is our multiplier when we're changing the temperature of water. Now there's a whole table here, and I'm going to get to that in a second here. Over here. Here is a whole table in which we need to know a lot of these substances. We need to know water, ice, and steam. And look at what it says here. Look, the specific heat capacities of water, ice, and steam, and air, there's air, are important and must be memorized. So water is 1 for imperial. It is 4.2 for metric. Ice has a specific heat capacity of 0.5 or 2 kilojoules per kilogram per degree Celsius. Steam is the same as ice. Look at that, they're the same. And air is 0.24 or 101. Now, before I carry on with anything else, for sensible heat equations, we have a formula we want to use. And that formula is the heat is equal to the mass of the substance, multiply that by the delta T, and remember that's a temperature change, and multiplied by the specific heat capacities. And these, let me just get a different color here. These are the specific heat capacities of these substances. And we're only going to be really concerned with these ones, yes? We're not going to be concerned with iron and lead and zinc. We're not going to do any calculation on those, okay? So these numbers are here. This is the specific heat capacity. This is the heat, and this is in BTUs or kilojoules. This is the delta T or temperature change. And this is the mass, and mass is always in pounds or kilograms. Okay, so that's how we're going to do all of our calculations for sensible heat. So again, sensible, which is not a change of state. It's just raising the temperature of a substance. We're going to use this formula. Okay. Any questions? All right. Now, they give us this define the following, and I think we're close. We already know that. And then what is the specific heat capacities of the following? You just have to follow along on that table, and you can fill those in. And that brings us down to, okay, we're not going to do latent heat yet. What I want to do is I'm going to do a bunch of examples using this formula with you. Okay, so here we go. For example, how much heat is required Okay, so how much heat is required to raise the temperature of 33.3 US gallons of water? That's a typical hot water tank. The one you put in grandma's house in the basement, the cheap ones, right? They're about 33 US gallons. And the incoming water temperature for Calgary is about 50 degrees Fahrenheit. And we want to raise the temperature of that water up to 140 degrees Fahrenheit. How much heat does it take to do that? So we are going to use our formula triangle that's right there. So here's our formula triangle where the heat is equal to the mass times the delta T times the specific heat capacity. So we have a capacity here. We need to know how many pounds that is. Remember, the mass is always in pounds or kilograms. So first thing we want to do is we're going to take the 33.3 US gallons and we're going to convert it to a mass. I know that there is 8.33 pounds in a US gallon. And so we come out with about 277, well, about exactly 389 pounds of water, yes? And we're going to multiply it by the delta T. So that's 140 minus 50. My delta T here is 90 degrees Fahrenheit. I'm going to multiply that by 90 degrees Fahrenheit. And then I'm going to multiply it by the specific heat capacity of water, which we determined earlier that water has a specific heat capacity of 1 BTU per pound per degree Fahrenheit. And if I multiply that out, that's going to be 24965 BTUs it takes, because you can see the pounds get canceled out, the degrees Fahrenheit get canceled out, and I'm left with BTUs. Pretty easy, huh? Let's do a couple more examples of this. Okay, I'll give you a second actually to finish writing it before I move on there. Okay, we got it? Yeah, all right. So I want to know how much heat required to raise the temperature of 50 cubic meters of water. I have a hot tub, and I want to know how much heat it's going to take to raise that 50 cubic meters of water from 10 degrees Celsius to 180. Oh, well, that's going to be too hot. 180 degrees Celsius cooking. To, let's go 90 degrees Celsius. How much heat is it going to take to raise my hot tub water, my 50 cubic meters of water, from 10 to 90? So the formula triangle will say that the heat is equal to the mass times the delta T times the specific heat capacity. So I need a mass to start out. 50 cubic meters of water. I know that there is 1,000 kilograms of water in a cubic meter. So I have 50,000 kilograms of water is my mass. Remember, we always have to start with a mass first. Then I'm going to multiply my delta T. So we go 10 to 90. So my delta T is 80 degrees Celsius. And then I'm going to multiply that by the specific heat capacity of water in metric. And that would state 4.2 kilojoules per kilogram per degree Celsius. And as you can see, the kilograms get crossed out, the degrees Celsius get crossed out. I'm left with kilojoules, and that's 50,000. And there is how much heat that takes. So do you ever come home from work or a holiday and it's winter time and somebody's turned down the furnace and it's quite cold? Well, that does happen sometimes. So for example, how much heat does it take I'm going to make this one more complicated because I can. How much heat does it take to raise the temperature of a room that has a square foot or a cubic footage or a volume of, okay, 8 feet high ceilings, 20-foot long wall, and a 10-foot long wall? Okay, so how much heat does it take to raise the temperature of a room with a volume of these measurements from, and I'm going to say it's pretty cold in there. Let's go 48 degrees Fahrenheit to a comfortable temperature, say about 72 degrees Fahrenheit. So I made this just a little more complicated because first off, remember our sensible heat formula is the heat is equal to the mass times the delta T times the specific heat capacity. Now, I have air. Well, wait a second, I have a volume of air. So I have to get a mass of what that air is first. So what I'll do is I'll get my volume of this room. So that's length times width times height is equal to the volume. So 8 times 20 times 10. So I got a volume of 1,600 cubic feet. And now I have to know how much air weighs. I know that air has a density of 0.076 pounds per cubic foot. Like so I will multiply that by 0.076 pounds per cubic foot. And this is just to get my mass of air. And I have a mass of air, and that's going to equal, what is it? 121.6 pounds of air. And now I got to multiply my mass. So the formula is mass times delta T times specific heat capacity. So there's my mass. My delta T is 48 to 72. And so that's a 24 degree Fahrenheit change. And then I multiply that by the specific heat capacity of air. So what that is, if I go back into that table way back here, the specific heat capacity of air is 0.24 BTUs per pound. So I'll go back to my formula here. So I'm going to multiply that by 0.24 BTU per pound per degree Fahrenheit. So that takes 29,000 or 2,918.64 BTUs to heat up that air. Okay. Okay, let's do one more before I get on to latent heat. So one more example.
How did you get 2,900?
Yeah.
Did I?
Yeah, I got a different answer.
My calculator funny? Maybe you're right. 121.
I got 700.416.
That's what I got.
That's what I got.
Yeah.
I see. You're right. I didn't times it by 0.24 at the end. You're correct. Thank you for that. Terrible example if I get it wrong. There we go. That's better. Forgot to hit the equal sign, I think, or something. Thank you for that. It's important. Now, we'll do one more before we go on. So here's one more. Okay, I'm going to give you a minute to do that right there on your own. So again, the formula triangle that we use is the heat is equal to the mass times the delta T times specific heat capacity. So the mass is 200 pounds. The delta T in here is from minus 25 to 32. So that's going to be 57 degrees is my delta T. And then we multiplied by the specific heat capacity of ice, which is 0.5 BTUs per pound per degree Fahrenheit. And if I type that out, it should come up to about 5,700 BTUs. We never did change the state. We just got to the melting point. That's all we did. Yes?
Okay, so Doug, I got to ask a quick question then.
Sure thing.
In the last one that you did where it asked for how much heat was required, you took the density of air and then you times that by the pounds or whatever. So I did why doesn't that work with changing it to the density of air for kilojoules? It's like 1.29.
Because this was in imperial, right?
So
This
then wouldn't you do this one in the not imperial, the other one?
no metric, no, because anything you have pounds, it's imperial measure.
Oh, it's already in pounds.
Fahrenheit is imperial measure.
If it wasn't like 200 pounds, if it was like 200 whatever, you'd have
Kilograms?
yeah, then you'd have to times it by 1.29, right?
Correct.
Okay, that's what I did. Okay, I understand where I went wrong. Thank you.
Okay, excellent.
It's already in pounds. You don't have to do anything. Okay.
That's correct. You already have the mass. That's correct. Before we had to find the mass. That's any questions? Any other questions? All right. So that brings us to objective 3. And this is where we start talking about latent heat. Now, by definition, latent heat is the heat that causes a change of state, not temperature. So we were calculating just changes in temperature, which is called sensible heat. To change the state from one state to the other. Now listen, we have ice to water, right? This one change of state. We have water to steam is another change of state. If we're talking about propane gas, we go liquid to vapor, which is a change of state. So the state has to change. And we know what the 3 states of matter are in, right? We know the 3 states of matter: solid, liquid, gas, right? So these are basically the changes of state that we have to be concerned about. Now, through scientific experimentation, they come up with these numbers, okay? And we'll go over this. I'm not a big fan of this little temperature change thing here, but here we go. So here's the 3 states of matter. And what we do is we give stuff some specific terminology when we change that state. So if we're going from a solid to a liquid, so ice to water, we're going to call it the latent heat of fusion. And if we're going from a liquid to a solid, meaning from water to ice, we're going to call that latent heat of solidification. If we go from water to steam, we call that latent heat of vaporization. And inversely, if we go from steam to water, or a gas to a liquid, we call that latent heat of condensation. So those just a little bit of more terminology associated with those changes of state. Okay, so I'm going to bring us right to the table. And this is a little more explanatory, this table. So this table outlines latent heat values, and it says right here, you should memorize the values for ice to water and from water to steam. And then it says, and for propane. But definitely ice to water and water to steam. And they give us 2 different values in here. One is for imperial measurement, and the other one is for metric measurement. Now, when we're doing latent heat values, we will use a formula, and I have a formula triangle for this as well. And the heat is equal to the mass times the latent heat value. So the heat is either in BTUs or kilojoules. The mass is always in kilograms or pounds, and the latent heat values are as follows. If I'm going ice to water, it takes 144 BTUs per pound of water to change the state. That's how much heat they calculated through experimental, whatever they did, they figured that out. Now, to go from water to steam, it takes 970 BTUs per pound, significantly more, but we are really vibrating those molecules to change it into steam. So it takes a lot more heat. And of course, the metric equivalence to both of these numbers is 335 kilojoules per kilogram, or 2,257 kilojoules per kilogram. And really, these are the ones I want you to memorize. The propane one will come into play in your third year in gas theory. Now let's do some examples doing calculations for latent heat. For example, so the question is, how much heat is required to change 100 pounds of water at 212 to steam at 212? We're not changing the temperature. We're only changing the state. So this is the latent heat of vaporization. And the formula up here says, take your mass, 100 pounds, and multiply it by the latent heat of vaporization, which is 970 BTUs per pound. Just like that. Nice and easy. Straight up. Okay. Let's do another example of latent heat. So, how much heat is required So I want to know how much heat is required to raise the temperature of 500 kilograms of ice to the melting point from minus 40 degrees Celsius. So, oh, wait, that's a sensible heat. Sorry, I need to change this question. I don't want to raise the temperature. I want to actually, I'm sorry, that's my fault. How much heat is required to change the state? That should be state. I got ahead of myself. And we're going to melt it of ice to water. I apologize for that. Here's my formula triangle where the heat is equal to the mass times the delta T, or times the latent heat value. So we have the mass, 500 kilograms. And we want to change this ice to water, latent heat of solidification, or the other one. And we times that by the number. Does anybody remember what that number is? Just shout it out if you know.
335.
335 kilojoules per kilogram. And that comes out to 16,750 kilojoules. 167,500 kilojoules of heat is required to change the state of ice to water. Sorry, I got the question all mixed up. Getting ahead of myself. And I'm getting ahead of myself because what's going to happen is we're going to combine both of these at the same time in the same question. So we'll have multi-steps to change a substance from ice all the way to steam. We're going to do multi-step equation here. And here we go. Here's the big questions. Okay, I want to know how much heat is required to change 3 pounds of ice at -15 to steam at 300. So we're going to go all the way through all of these. And this is how, or this is the steps I use for this. Now, first off, I have 2 formulas. One is sensible heat, where the heat is equal to the mass delta T specific heat capacity. The other one is latent heat, where I'm going to take the heat is equal to the mass times the latent heat value. So there's my 2 formulas. So when I'm doing one of these questions, I always have a little piece of paper, and what I do is I kind of draw a temperature scale on there. And I put my numbers on here. So I have -15. And then what is the freezing point again? I think it's 32. I always write that down. And then I write the boiling point, 212. And then I'm going all the way up to 300. So what I do is I write these down so I can see where they go. And then I can now start my equation. So the first step, I call this number 1. The first step is to take that ice and bring it up to the melting point. So this is a sensible heat equation to get that ice to the melting point. Sensible heat would say, take your mass, 3 pounds, multiplied by the delta T. So that's the temperature difference between these two, which is, let's see, that's going to be 47 is the delta T between these two. So 47 degrees Fahrenheit. Then I multiplied by the specific heat capacity of ice. And that happens to be 0.5 BTUs per pound per degree Fahrenheit. Now, if I multiply that out, that's 3. Comes out to what? 70.5 BTUs, yes? So now what I did is I have right here, I have this ice at the melting point. So I'm going to then add latent heat to it to get it to water, right? I need water. So now I'm going to use the latent heat formula. I'm going to call this step number 2. And it says, take your mass, 3 pounds, multiplied by the latent heat of fusion, solidification, which is 144 BTUs per pound. These are our multipliers. That's 432 BTUs. Now I have water at 32 degrees Fahrenheit. So I need to raise the temperature of this water to the boiling point. Raising the temperature, so this is a latent heat. Now I have to go sensible heat. I'm raising the temperature of the water, and my delta T in between there is 180 degrees Fahrenheit between these two. So step number 3, I'm going to raise the temperature of that water to the boiling point, and that's sensible heat. So it says take your mass multiplied by the delta T, which is 180, multiplied by the specific heat capacity of water, which is 1 BTU per pound per degree Fahrenheit. And that is 540 BTUs. Now I have water sitting there at the boiling point. This is going to be a latent heat equation right here, where I'm going to change the state of that water to steam. I'm going to call this number 4. Latent heat says take my mass and multiplied by the latent heat value of vaporization condensation, which is 970 BTUs per pound. And that is 2,910 BTUs. Now I have steam at 212. We need to go to 300. This is going to be a sensible heat. We're just raising the temperature of the steam. And I'm going to call this number 5. There we go, 3 pounds multiplied by the delta T. The delta T in between these two is 88 degrees Fahrenheit between this and this. So it's 3 times 88 degrees Fahrenheit multiplied by the specific heat capacity of steam, which is 0.5 BTUs per pound per degree Fahrenheit. And that comes out to 132 BTUs. Now, the last step is to take all of my heats and add them together to get the total heat. So the total heat $540 plus 432 plus 70.5. The total heat is 4,084.5 BTUs is what it takes to take that 3 pounds of ice at minus 15 to steam at 300. So here comes the example for metric. I'll write it down here. Oh, let me use a black pen. So I want to know how much heat is required to change 300 kilograms of ice at -3 to steam at 400. Now, what I'm going to do is I'm just going to write out the steps, and I'm not really going to say too much. I'm just going to do my thing and write out the steps. Okay. And here I go. So now, did you get the same answer as me? So in the book here, it shows, so sensible heat to get it from freezing to the, or when it's frozen to the freezing point, latent heat, and then sensible heat, and then latent heat, and then sensible heat. They just do it on a different scale, but I did it just with a straight up scale, numbering them as we go. So it's very much the same as this, only slightly different. Okay. And then it brings you to all types of questions in here with examples. As you can see in your book, there's a lot of different examples in here. And then it brings you to another page. And then that would come to the self-test. So now what I want you guys to do is start the assignment that I'm going to give you.